Welcome. Today we are exploring advanced architectural synthesis, a deep dive into the evolution of modern software design. On the left side of this visualization, we see the monolithic structure. This model is defined by coupled components and a centralized database, forming a rigid, grid-like framework. While this provides a high degree of predictability, it often leads to significant bottlenecks and scaling challenges as the system expands. As we move toward the right, we witness a transition into mesh infrastructure and distributed systems. This paradigm shift introduces decoupled microservices and an event-driven mesh, allowing for greater agility and resilience. In this environment, data segregation becomes a critical strategic choice, ensuring that individual services can operate and persist data independently. This diagram serves as a strategic trade-off analysis, illustrating how we navigate the complexities of data segregation and mesh infrastructure to build the next generation of robust, scalable, distributed systems. The architectural metamorphosis from monolithic entities to distributed microservices has fundamentally redefined modern software engineering. While this transition successfully addressed the need for organizational agility and independent scaling, it introduced a new paradigm of challenges. As illustrated by the comparison between unified complexity and distributed complexity, we have moved from managing a single, cohesive entity to managing a vast web of interconnected components. This evolution highlights two primary bottlenecks that teams must now navigate. The first is distributed data management, which involves the loss of immediate consistency and the inherent difficulty of joining data across distinct service boundaries. The second is inter-service communication, representing a shift from reliable in-process function calls to network requests that are inherently subject to failure and latency. In essence, we have not eliminated the difficulties of system design. We have traded a single, unified complexity for a far-reaching distributed complexity.
CQRS, or Command Query Responsibility Segregation, introduces a functional split between how we write data and how we read it. By separating the input stream into distinct command and query paths, we can optimize each for its specific needs. The right side focuses on command operations, prioritizing data integrity and the strict enforcement of domain invariance within the database. Conversely, the read side focuses on queries, where we prioritize latency reduction and user experience optimization, often using specialized read models. This architectural approach is ideal for systems with highly skewed read-to-write ratios, such as e-commerce platforms, where thousands of product views may occur for every single purchase transaction. Event sourcing represents a fundamental shift in how we manage data, acting as the temporal backbone of modern systems. The core concept is simple yet profound. State is not a static snapshot. Rather, it is a history of everything that has happened. There are two primary mechanics at play here. First, we store immutable facts, events like order created or item added, that cannot be changed once recorded. Think of these as individual frames on a film strip, as illustrated in the center. Second, we use reconstitution, which involves replaying these events in sequence to derive the current state of the system at any given moment. This approach offers significant strategic benefits over traditional CRUD snapshots, which are often insufficient for complex business requirements. By maintaining a full history, we gain the power of time travel, allowing us to query and reconstruct past states with absolute precision. Furthermore, it creates unassailable audit trails, providing a complete and verifiable record of every action and transition within the application. When adopting distributed data architectures, it is essential to account for what is known as the complexity tax. While these systems offer significant benefits in terms of scalability and auditing capabilities, they also introduce a heavy burden of technical and operational challenges. This balance is rarely equal, and the costs of adoption are substantial. First, we must contend with eventual consistency, which requires sophisticated strategies to manage the lag between data being written and subsequently read. Second, we encounter versioning hell, where performing schema migrations on immutable event logs becomes a complex, high-stakes endeavor. Finally, there is the increased operational overhead required to maintain the necessary infrastructure, including message brokers and projection engines. As Martin Fowler famously cautioned, for most systems, implementing CQRS adds a level of risky complexity that may outweigh its intended benefits.
we must carefully evaluate whether our specific needs truly justify the cost of this tax. When designing microservices, we often face the challenge of querying data spread across multiple domains. We have two primary strategies to address this: API composition and CQRS. Option A is API composition, also known as the gateway approach. Here, an API gateway serves as an orchestrator. The main benefit of this mechanism is its simplicity. However, the system's performance is strictly bounded by the slowest service involved, which can lead to increased latency in complex environments. Option B is CQRS, or Command Query Responsibility Segregation. This strategy utilizes projections to optimize read operations by separating them from write operations. In this flow, the write service publishes events to a queue whenever data changes. These events are then consumed to update a specialized read database, creating pre-calculated views optimized for specific query patterns. This allows the user to retrieve data with extremely high performance. The trade-offs for this efficiency are a higher implementation cost and the potential for data staleness due to the nature of eventual consistency. Change-driven architecture is emerging as a compelling alternative to traditional event-driven designs. Currently, many organizations face what we call the event tax, the substantial overhead incurred when developers must refactor or rewrite existing applications just to emit events for downstream systems. This adds significant complexity and slows down the delivery of new features. The solution, exemplified by platforms like Drosy, involves using continuous queries that tail the database changelog directly. As you can see in the diagram, instead of the application pushing events, the system observes the database in real time. This creates a seamless, real-time change stream that feeds directly into downstream components, such as the monitoring dashboard shown on the right. The primary benefit of this approach is a low-cost dependency inversion. It allows us to build reactive, responsive systems without the need to refactor the persistence layer or modify legacy application code. It decouples the notification of changes from the business logic itself, making the entire architecture more flexible and easier to maintain. The service mesh layer represents a fundamental shift in how we handle connectivity within modern architectures. The core concept at play is the decoupling of the network from the application. In a traditional setup, developers are often forced to embed complex networking logic, such as retry mechanisms, mutual TLS for security, or circuit breaking for resilience, directly into the application code. This approach creates heavy, brittle services that are difficult to manage at scale. By introducing a service mesh, as illustrated in this diagram, we create a clear separation of concerns. The bottom layer represents the pure application logic, where developers focus exclusively on business functionality. Above this sits the mesh infrastructure, a dedicated layer that transparently handles all inter-service communication. This architecture provides three critical capabilities without requiring changes to the application code: robust security through automated identity and encryption, comprehensive observability into how services interact, and sophisticated traffic control for advanced routing and reliability. This decoupling allows the underlying infrastructure to evolve independently while ensuring consistent performance and security across the entire application ecosystem. The standard approach to managing service mesh functionality is through the sidecar pattern. Under this mechanism, every service instance is paired with its own dedicated proxy, such as Envoy, which resides alongside the application container within a single Kubernetes pod. This architecture provides excellent isolation and offers polyglot support, meaning the mesh features work seamlessly regardless of the programming language used for the service. However, this model introduces what is often called the sidecar tax. As clusters scale, the cumulative CPU and memory overhead of running thousands of individual proxies can become substantial. Additionally, because the proxy and application are co-located in the same pod, updating the proxy often requires a full restart of the application, creating operational friction and potential downtime. The sidecarless evolution, known as ambient mesh, represents a fundamental shift in service mesh architecture. The central concept involves moving the proxy from the individual pod level directly to the node. In this model, multiple services, such as Service A, B, and C, share a single L4Z tunnel. This shared proxy provides a secure overlay and ensures zero-trust security through MTLS. Let's examine the trade-offs between performance and maturity in the data plane battle. When comparing latency, we see a significant gap between traditional and emerging architectures. The sidecar mesh, while providing mature security, incurs a latency of approximately 0.63 milliseconds. In contrast, ambient mesh at layer 4 and Cilium eBPF-based solutions drastically reduce this overhead to around 0.15 to 0.16 milliseconds by leveraging kernel efficiency. However, performance is not the only factor. Sidecars offer the strongest isolation, ensuring that a compromised pod does not lead to a compromised mesh. While Ambient's shared node agent optimizes for cost and speed, it alters the failure domain, which is why its security model is still considered to be evolving. Ultimately, the choice depends on whether your priority is the highest level of proven isolation or the lowest possible latency.
Pragmatic optionality helps us determine when the sidecar pattern transitions from a choice to a requirement. The primary factor in this decision is whether your infrastructure involves mixed environments or a polyglot monorepo. If the answer is yes, a sidecar becomes mandatory. Its role here is to ensure parity across local, staging, and production environments by handling the necessary adaptations. Conversely, if you are not dealing with such environmental complexity, you might instead opt for ambient services or traditional libraries. When we view the sidecar as an adapter, its value becomes even clearer. In a production environment, the sidecar takes on heavy lifting tasks like MTLS and centralized logging. In a local development setup, that same sidecar can be bypassed or run with a null configuration. This decoupling is essential because it keeps the core application code pure, allowing developers to focus entirely on business logic without worrying about the underlying networking or security infrastructure.
This matrix synthesizes various data architecture patterns based on two primary dimensions: complexity and the requirement for audit or historical tracking. On the horizontal axis, we move from low architectural complexity on the left to high complexity on the right. On the vertical axis, we transition from simple state consistency at the bottom to strict audit and history requirements at the top. Starting in the bottom left quadrant, we have CRUD. This represents our baseline architecture, ideal for systems with low complexity, where maintaining the current state is the primary objective, and simple consistency is sufficient. Moving to the top left, we find change-driven architectures, such as DROSI. These patterns are best suited for environments where complexity remains relatively low, but there is a clear necessity for a strict audit trail or the ability to react to state changes in real time. In the bottom right quadrant, we encounter CQRS, or Command Query Responsibility Segregation. This pattern is designed for high-complexity systems, where separating read and write models is necessary for performance and scalability, even if strict historical auditing is not a primary requirement. Finally, in the top right quadrant, we have event sourcing. This represents the most comprehensive approach for systems requiring both high complexity and a definitive, immutable record of every state change. By treating data as a continuous stream of events, much like a film strip, it provides the highest level of auditability and historical reconstruction. This decision matrix serves as a framework to help align your choice of data architecture with your specific operational needs and domain complexity. To help synthesize our findings, this decision matrix outlines the optimal use cases for different mesh infrastructure models. You should choose the traditional sidecar approach if your organization requires absolute zero-trust isolation at the pod level, or if you are navigating strict regulatory compliance mandates. It remains the best choice for those needing mature, multi-cluster support immediately. Conversely, move toward an ambient or sidecar-less architecture if your primary driver is the reduction of cloud infrastructure costs, specifically in terms of CPU and RAM utilization. This model is ideal for greenfield deployments, or when your main requirement is L4 security via MTLS without the overhead of L7 complexity. Finally, consider a gRPC or library-based approach for applications with extreme low latency requirements, where you need full control over the entire code stack. Modern architecture is fundamentally about the art of balance. It is a common misconception that our primary role is to simply select the best technology available. In reality, architectural excellence lies in managing the inherent tensions between competing priorities, specifically the trade-offs between simplicity and scalability, and the classic dilemma of consistency versus availability. Our objective is not to design the most technically advanced or complex system possible. Rather, we must strive for an architecture that strategically aligns technical costs with actual business value. Every architectural decision carries a price, and our goal is to ensure that the complexity we introduce is always justified by the value it returns to the organization. This perspective is a core tenet of advanced architectural synthesis.